Welcome back to Chapter 3. This section 4, we are going to learn about what are called arithmetic sequences. Now you might be looking at that thinking that's not arithmetic, that's arithmetic. Well, arithmetic is just the adjective for arithmetic. And arithmetic, what that means is adding and subtracting. And so arithmetic sequences are sequences where we're just adding and subtracting stuff. And you might be thinking, well, what is a sequence? We're about to get there, don't worry. So our learning targets is I can identify and describe arithmetic sequences. And we're going to be describing them both explicitly and recursively. And we'll also use a few other nice big words. So arithmetic sequences, what are they? So before we get to what an arithmetic sequence is, let's look at what is a sequence. A sequence is just an ordered list of numbers. Generally, it forms a pattern. They're separated by commas. And so any list of numbers separated by commas is a sequence. Now, it has to really kind of form a pattern for it to matter. One of the most famous sequences has a name. It's called the Fibonacci sequence. It looks like this. It's 1, 1, 2, 3, 5, 8, 13, 21, 34, and then it keeps going. And so when we're looking at sequences, a lot of times we think like, well, how do we get from one to the next piece? And so the Fibonacci sequence starts out with two ones, and then the next number is the sum of the two previous numbers. That's the pattern here. So 1 plus 1 equals 2. 1 plus 2 equals 3. 2 plus 3 equals 5. 3 plus 5 equals 8, etc. So the next number in the sequence is going to be 21 plus 34 is 55. The next will be 34 plus 55 is 89. And it just keeps going like that. Now that's a pretty complicated sequence, and it's way more difficult than an arithmetic sequence, which is what we're going to be looking at for the majority of today. An easier type of sequence here would be something like this: 4, 7, 10, 13, 16, 19, 22. Well, as you're looking at that, you're probably thinking like, well, how do I get from one number to the next? That's kind of a natural thought process for people to go through. We're always looking for patterns. It's part of being human. And so to get from a 4 to a 7, well, we're just adding 3. To get from 7 to 10, we add 3. To get from 10 to 13, we add 3. To get from 13 to 16, we add 3. 16 to 19, we add 3. 19 to 22, we add 3. That's a way easier pattern than the Fibonacci sequence. We're just always adding 3 each time. That is an arithmetic sequence. An arithmetic sequence is defined as a sequence that has a common difference. The common difference is that. Common difference. So a common difference is if you take a term minus the term before it, you always get the same number. And a term, each number in a sequence is a term. So for our arithmetic sequence here, we have the first term, the second term, the third term, the fourth term, the fifth term, the sixth term, the seventh term. We could find the eighth term, that's just 22 plus 3, that's 25. And so each of these pieces are called terms. Again, an arithmetic sequence, it just means if you take a number minus the one before it, you always get the same thing, and that's called the common difference. A lot of times we're going to use a variable. The common difference is usually a d. Why would it be a d? Well, it's the common difference. That one actually makes sense. They don't always make sense, but that one does. So we have some notation for sequences. The notation is sometimes really similar to the function notation that we saw in our last topic, and sometimes it's a little bit different. First of all, the term number is n. So n is whatever the term number is, and that is the same thing as the x's that we have used when dealing with functions in a general notation type sense. Now, The difference between an n and an x is in the implication. X implies that this is going to be a continuous variable. We can have all sorts of stuff in between. N implies it's going to be an integer. We can have the first term, we can have the second term, we can have the third term. We're not going to have the 1.7th term. That doesn't work. So a sequence is going to be a discrete thing because we'll jump from the first to the second to the third to the fourth, etc., etc. And so n implies that it's going to be discrete. And we use n because it's the term number. A specific term could be a of n. So this is very similar to function notation. Now, and we can label our sequences by different letters, or generally a capital letter, and we usually start with A. Why would we start with A? Because it's the beginning of the alphabet. I know usually we start somewhere in the middle for whatever reason, like our functions, we start with f of x because that's the function of x. Sequences, we start with A. So this could be sequence A, and this one could be sequence B. And so this would give us our term number. So if we wanted A of 4, that would be the fourth term of sequence A. That would be 1, 2, 3, 4. So that would be, it would just be 3. We could do the fourth term of sequence B. That was 13. So these, like this notation is very, very similar to function notation. Again, the only real difference is that the function is going to be more of a continuous one, where a sequence is discrete, where we wouldn't have a of 0.7. Like that doesn't make sense. We could have a of -1. We could have what would be the negative first term in the sequence. Usually we don't. Usually we start with the first term, but we could follow the pattern backwards. It's just a possibility. Another way of notating a specific term, as opposed to using this function notation type, we can use a subscript notation. So a of n would be the nth term of sequence A. So in this case, we could have a of 4 is 3. These two things are exactly the same. Now notice in this one, it's not a capital A, it's a lowercase a, because each term in the sequence, like each term is going to be a lowercase letter, where the sequence itself is usually an uppercase, or sometimes it'll do like an A of 4 where it'll use the lowercase letter, but it'll stretch it so it's as big as an uppercase letter. Just things that it does. So we could have A of 4, we could have B of 4 is 13. These two things are the same. They mean the same thing. So if we have a sequence A, it's going to be A1, A2, A3, A4, whatever. Like, so that's the first term, the second term, the third term, the fourth term, etc. You wouldn't generally write this out because it gives no meaning to it, but that would be the generic sequence. And this stuff is true even if it's not an arithmetic sequence. That's just general sequence stuff. And so one of the things that we're going to do is we're going to be writing formulas for our sequences. Now, we have two types of formulas that we use for sequences. We have recursive formulas and we have explicit formulas. A recursive formula is a formula that uses previous terms. A lot of times it's just the previous term, but it could use multiple previous terms. The Fibonacci sequence that we just looked at, that was a recursive thing because we used, each term was the sum of the two terms before that. An explicit sequence or an explicit formula is based off the term number. So if you have the fifth term, you'd plug in the number 5 and it would give you what that term was. An explicit formula is very similar to the equations that we've been looking at recently. Those are called explicit equations. They're based off of x, not off of what came before that. Generally speaking, recursive formulas are easier to make because you're just looking at how do you get from one number to the next. However, if you wanted to find the 47th term, you would need to know the 46th term, which means you need to know the 45th term, which means you need to know the 44th term, etc. So you have to start and you have to work your way and build the sequence all the way up to that point. Whereas if you wanted to know the 47th term in an explicit formula, you would just plug in 47 and you would get whatever that term is. So it's usually a little bit tougher to create, but it can be more useful to finding terms that are a ways in the distance. And so all of that is just sequences in general. Now, to narrow it down to the arithmetic sequences that we're going to look at, a recursive formula. So with an arithmetic sequence, every time you're always adding the same number, that common difference. So a recursive, we'll take our sequence again. We're going to make these. A recursive formula, we have to have our first term. We need a starting point. And then all this says is that an, the number we're looking for, is an minus 1, that's the previous number, plus that common difference. So if we were going to make a formula for this arithmetic sequence, we would need a1, the first term is 4, right? We see that right here, a1 equals 4. And then an equals an minus 1 plus, what did we do each time? We had to add 3. So our common difference is going to be 3. So it's the term before plus 3. So if we wanted the next term, 22 plus 3 is 25. If we wanted a term after that, 25 plus 3 is 28. And we could keep going. So that's all you have to do to make a recursive formula in for an arithmetic sequence. This is going to be an, this is going to be an minus 1. All that means, this is the previous term. So if we wanted to find the 7th term, that would be the 6th term plus 3. For an explicit formula, we have this equation, an equals a1 plus d times n minus 1. Now, this should look kind of familiar. For instance, we can take this a1 and move it to the other side of the equation. So an minus a1 equals d times n minus 1. If we change these variables back into things that we have seen before, this would be y. An is our y, that's our function, minus the first term, I'm going to call that y1, equals d. D, this common difference, this plus 3, what does that look like? It's a change to go to the next value. That's the slope times x minus x1. This is point slope form of a line. We've done this. That's all it is. And you can do it. Technically, in this one, we use specifically the first term. So we have n minus 1, and we have the first term. So if we were to make our equation here that we're looking at, we have an equals a1, the first term is 4, plus d, 3, times n minus 1. We could have started with any point. So let's say we know that the fourth term is 13. So we could have 13 plus 3 times n minus 4. These will be the same. If we multiply that out, it's going to come out to the same thing that would look like slope-intercept form. We'd have y equals mx plus b. It would be y equals dx plus the 0th term. Why don't we use the 0th term? Because the 0th term doesn't usually mean anything. We start out with the first term because that's the first one. But we could follow it a term back. What would the term before 4 be? Well, we're always adding 3, so we just have to subtract 3. It would be 1. So either of these, when we multiply it out, we'd get an equals 3 times n plus 1. So that's how we can make a recursive formula and an explicit formula. So here's another sequence. In this one, we have number of days rented and the rental cost. This would be the term number, and the rental cost is the an. So this right here is the sequence. The y values are the sequence. The 1, 2, 3, 4, that's just term 1, term 2, term 3, term 4. All right, so I know we just did one of each of these. Go ahead and try to write this both recursively and explicitly. I don't have a pause thing up here, but I'm just going to tell you to go ahead, pause your video, write an explicit formula, and write a recursive formula, and then we'll go through it so you can check to see if you know what you're doing. So pause your video now. Did you do it? If you didn't, go back and do it. Again, this is part of the learning process. You want to try it because it always makes a lot more sense when somebody's showing you. It's when you try it and you're like, oh, wait, what happened here? That's when you get those questions. So if you haven't done it yet, pause it and go back and do it. All right. Well, if you still haven't done it, there's not much I can do to get you to do it. So first, let's look to see what is our common difference. So to go from 26 to 38, it's not quite so easy to add. We can subtract. What's 38 minus 26? Well, that's 12. 50 minus 38 is 12. 62 minus 50 is 12. All right, so our common difference is 12. All right, recursive formula, we need a1, the first term, was 26, and then an will equal an minus 1 plus our common difference of 12. So if we wanted the fifth term, we would take the fourth term, which is 62, plus 12 to get 74. Now, if we want to know how much would it cost to rent this for a month, we'd have to find all the way up to that 30th term, and that's less than pleasant. That's where the explicit formula comes in. So here we have an equals a1. What's our first term? Well, that was 26, plus the common difference was 12 times n minus 1. And there we go. That's the explicit form. Now if we wanted to figure out what it was to get to the 30th, we can go 30 minus 1 is 29 times 12 is a bigger number. It's 290 plus another 58, so 348. And then plus 26 gives us 374. So $374, as opposed to finding each one along the way. Yeah, so that's formulas. Did you get those two right? If not, did you see where you made your mistake? Now we can go between equations as well. If we have an explicit formula, or we want to write an explicit formula from a recursive formula. So we have a recursive formula We have heights of stairs. It's shown as an equals an minus 1 plus 4, and a1 equals 7. How could we find the explicit formula? Well, for this, we get the 4 there. That tells us d equals 4. And we know a1 equals 7. So our explicit formula, an equals a1, which is 7, plus our d, 4, times n minus 1. That's all it is. And so now if we wanted to figure out how tall it was for the 1, 2, 3, 4, 5, 6, a whole bunch, it looks like there might be 21 steps in there. So what would A21 be? We wouldn't have to go through and find every single one of them. We can go 7 plus 4 times 21 minus 1. 21 minus 1 is 20. So we have 7 plus 4 times 20. 4 times 20 is 80, plus 7. A21 equals 87 inches. So that 21st step will be 87 inches above the initial ground level. So going from a recursive formula to an explicit formula, again, you just pick out the two things that you need in order to write the equation of the formula, and you're good to go. How about going the other way? Going from an explicit into a recursive formula. So we have our formula here. An is 1 plus 1/2 n. So for a recursive formula, we need two things. Remember, recursive formula, we need a1, and then an is going to be an minus 1. That stays exactly the same, plus the common difference. Well, what is the common difference? The common difference is the slope. What's being multiplied to n? So in this case, it's 1/2. Then we need a1. This is not in the same exact format as the other ones that we've looked at, because we don't have an n minus 1. We just have 1/2. So how do we figure out what a1 is? How do we figure out the first term? We just plug in 1. a1 will equal 1 minus 1/2 times 1. 1/2 times 1 is 1/2, so 1 minus 1/2 is 1/2, so a1 is 1/2. And the common difference, which is the same as the slope, is 1/2. So a1 equals 1/2, an equals n minus 1 plus 1/2. So recursive formulas are really good if you have to write out the first few terms. So if we wanted to write the first few terms, we start with 1/2. And then each time we're going to add 1/2. So 1/2 plus 1/2 is 1, plus 1/2 is 3/2, plus 1/2 is 2, plus 1/2 is 2.5 or 5/2, etc. So plus 1/2 is 3. And we can keep going from there. And so that's what arithmetic sequences are. With any sequence, we have recursive and explicit formulas. Again, the recursive ones are generally easier to make. However, explicit formulas will get us those terms wherever it is that we want them. But for arithmetic, they both have fairly simple formulas, and an arithmetic sequence is just linear. It's basically a linear function. It's just not continuous. So that's what we're working on this section. I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.